hide this problem. A liquid level controller is shown in the figure given below. Level transmitter is direct acting. Level transmitter is direct acting. And valve is A to open. What type of control action should the controller have and why? So what is the control action of the controller and why? What is the reason for that? What is the type of control action? Is direct acting, indirect acting? Direct acting. LT stands for level transmitter. Suppose let's say the system is here and then control valve is, let's say 30% open. Now let's assume that level is rising. Level is rising. Then, so let's mark the responses here. This is A, this is B, and this is pressure signal. Suppose if the level increases here, if the level increases here, then what should be the valve opening? Should it increase or decrease? It should increase, because you to bring back level to back to the same point, the level has to increase. So that is the fundamental. So the fundamentals you have to remain. That means if the level increases beyond the set point, the control valve has to open more. So that means if A increases, so the percentage of opening should also increases. So pressure and then percentage of opening. Now if A increases, B will also increase. No, B will also increases, because A and B are, LT is direct acting. Now to open the valve, should the pressure increase or decrease? Should the pressure has to increase, because it is A to open type. So across the LC, if you see, the input increases, output also increases. So that makes the system direct acting. Is it clear to everybody? So basically this is, so the controller, you have controller. See, if input increases, whether the pressure increases or let's say decreases. If input increases, then the pressure increases, direct acting. If input increases, pressure decreases, it is indirect acting. That is how you have to decide. The next topic is controllers, types of controllers. So there are 4 types of controllers. Proportional controller, proportional integral controller, proportional derivative controller, proportional integral derivative controller. These are the 2, 3, 4 types. You call it as P, PI, PD, PID. Proportional controller, proportional integral controller, proportional derivative controller, proportional integral and derivative control. So what is the input to a controller? Controller, what is input? You are getting field measurement and you are getting a set point. So what it does is it generates error. In the block diagram, if you see, what is actually the controller generates is error. So that means your set point R and your measurement M, R minus M. So it generates. So basically what is input to the controller is an error. Error. And what is the output to the controller is the pressure signal. Pressure signal. So the controller transfer function is it receives the error and it generates the pressure signal. So what is input to the controller is error. But how does error is generated is set point minus the field measurement. Clear? Now let's see different type of controllers. First, how does proportional controller works? How does the proportional controller works? So here the equation is pressure is equal to steady state pressure plus Kc into error. So this is the equation. What is steady state pressure? Now go back to your CSTR example. In your CSTR example, you need to send 1 ton per hour of the cooling water flow rate. That is the steady state. So for sending 1 ton per hour of cooling water flow rate, what is the valve opening? 30%. So for the 30% of opening, what is the pressure required? 7 psi. So that 7 is your steady state pressure. That means when the system is at steady state, what is the pressure that the controller is delivering is the steady state pressure of the controller. So when the entire system is at steady state, so now if you take the CSTR example, CSTR, now go back to the first class. CSTR, we have a release of, let's say, 100 joules of energy, and out of that 100 joules, we have, let's say, 60 joules we are consuming internally, and our 40 joules we are consuming internally because feed is coming at 40 and the reaction is 60 degrees. So you have to consume part of the heat, and rest of the 60 joules you need to remove. That 60 joules, how you are removing is using the cooling water. So how much cooling water you are flowing is, for that 60 joules we have calculated cooling water flow rate, that is MCP delta T. So that MCP delta T is, what is the inlet temperature is 35, outlet temperature is 45. You have calculated how much cooling water is required. So that is 1 ton per hour. So that 1 ton per hour cooling water flow rate corresponds to 30% opening. So I'm just saying some arbitrary numbers just to get acquainted with the system. So that 30% opening, how much pressure required is 7 psi. Are you getting that example when I am saying with the words, or are you confused? That's CSTR. Clear. So that is what is your steady state pressure. How do you generate transfer function? what is transfer function? Actual variable minus PS is equal to Kc into, this is error minus what is steady state error. When the system is at steady state, what is error is 0. So capital P into Kc into capital E. So what is the transfer function? Apply Laplace transform on both sides. Kc into U of S. So P of S by E of S is equal to Kc. So the transfer function of the controller is Kc. What do you call this? Kc is controller gain. Controller gain. What do you call this Kc as? Controller gain. Just write up to this point. Next thing is, let's say, how does, let's say, P controller works. Let's take, now I'm taking the same example of CSTR. I'm not going to draw the picture again. Let's say CSTR example. CSTR example. Let's say my field measurement is 59 degrees. That means what is the error? Error is equal to R minus M, which is 60 minus 59, which is 1 degree. Actually, I am representing actual values. Ideally, what is my field value is 59 degrees, means what is my deviation variable is minus 1. Because steady state is 60, 59 minus 59 degrees minus 60 is minus 1. So what is my set point is 0. So just to get the understanding, I am putting the actual values. Now, how does the controller works? Now, how does the controller work? See, let's take Kc equal to 0.1. If I take Kc equal to 0.1, then what is my pressure signal delivered by the controller is, pressure signal is equal to, let's say steady state pressure is 7 plus 0.1 into 1. So the 7.1 PSI is the controller. Now the control valve, let's say, now this is the signal which goes to field. Now the control valve opens 32%. So because what is steady state? Steady state is PSI is equal to, or let's say PS, steady state pressure is 7 PSI, control valve opening is 30%. This is what is my steady state. Now, when I get a field signal of 59, I will calculate my error, and then that error is equal to 1 degree. So that 1 degree, that means 7 plus 0.1 into minus 1, 7 minus 1 PSI, and the control valve opens 32%. So when the, let's say this is how, so this is my, let's say 60 degrees. It drops because of some reason to, let's say 59. Now you are receiving a pressure signal of, let's say 32, which is, sorry, it should close. No, the valve is should close. The valve is 28%. Control valve closes to 28%. Then this sends less cooling water. Then that means it will come back to. So here there is a question whether this 28% is open, or whether this 28% is sufficient to bring back it to 60 or not is a question mark. So, but this is how the response. So the system is 60 degrees, drop it to 59. Since you closed the control valve, then it takes a reverse direction and then it settles somewhere. Suppose if it settles at, let's say, 60 degrees, then what is your offset is 0 because it deviated from 60, you bring back to 60 degrees. Suppose if settles at 59.8, then what is your offset? 0.2. Now let's take another case. This is if you put Kc equal to 0.1. Suppose if I put, let's say, Kc equal to 1, then what happens? What is my pressure signal? 7 into 7 plus 1 into 1, which is 8 psi. So that 8 psi means what? The control valve closes here to 25 percentage. Now where the response will be faster? Now this is, let's say, Kc equal to 0.1. Now see here, what happens is the system comes to steady state early because your valve opening is 25%. That means the system's response is fast. When Kc equal to 1, the system response is, let's say, fast. So that is why what I wanted to conclude here is when Kc increases, the fastness of the system also increases. When Kc increases, the fastness of the system increases. But there is one problem. When you go to very high values of Kc also, there is one problem. I'll tell you later on. This is just to demonstrate that what is the value or what is the impact of Kc. What is the impact of Kc is, if it increases, the response will become faster. Because for the same error, if I have Kc equal to 0.1, valve is closing from 30 to 28%. Suppose for the same error, if Kc is equal to 1, the valve is going to 25% closer. So 25% closer will have a faster response than 28%. Today will be mostly theory topic. Yeah, that means if Kc increases, offset also decreases. That is why when we are solving the offset problems, you will generally get m by 1 plus 2 Kc. So that is where I told, if Kc increases, offset decreases. Just understand this concept. See, all these are random values that I am explaining so that you will get the concepts. So don't just take that like how I am calculating all this stuff. Okay. Directionally, it should be same. Qualitatively, it should be same. Quantitatively may not be correct. Now suppose since Kc increases, so the fastness increases. So somebody is in, let's say, so very optimistic or let's say very curious, has put Kc equal to 100. Then what happens? Kc equal to 1000 somebody has put. Then what happens? Or Kc equal to 100 is also fine. Then if my error is equal to, let's say, 1 in this case, then what happens to pressure signal is, this is 7 psi plus 1 into 100. So it has become 107. Valve fully closes. Valve fully closes. This is an air to open type. That means, so that means this is air to close type, because we need a fail close situation, fail open situation. No, this is an indirect type of valve. So somebody has put Kc equal to 100 when error is equal to 1. So this is the pressure signal. When valve fully closes, then what happens to the temperature? So this is my 60 degrees. So suddenly it becomes 59 degrees. So when you close the valve fully, what happens to the temperature? Temperature increases rapidly. So at one point of time, it has become 61 because temperature is reaching, no, it doesn't reach 100. But when temperature becomes 61, then what happens to my measurement? 61. Then what happens to my error? 60 minus 61. So error has become -1. Then what happens to my pressure signal? 7 minus 1 into 100. So it becomes, let's say, minus 93. So that means the valve get, let's say, minimum signal. So you will get minimum signal. That means valve goes to fully open. So the valve goes, so because of high value of Kc, because of high value of Kc, valve, or let's say the controller makes the valve on off like this. So this is called as, that is why this controller is also called as on off controller. When the value of Kc is extremely high, the valve goes to open close. This is called as chattering of the valves, which is dangerous situation, because this will reduce the life of the control valves. Because when the valve closes, the stem touches the base. When valve opens, stem touches the base. So it is frequently touching the base. So the life of the valve goes. So it doesn't go to 107. So just I'm saying anything, any value higher than 30 psi, the valve goes to fully closes. 15 psi. So pressure 107 means it cannot go to minimum more than 15. No, the maximum signal is 15 psi. So 107 means it already crossed 15. No, so that is the valve goes to fully closes. Here some value. So the valve goes to full open. So that is why when the high value of Kc is there, the valve becomes, the control becomes extremely difficult, or the controller lost the control. The controller becomes extremely sensitive and lost the control over the system. So did you get what is proportional controller is? But what is the main point of proportional controller is, it just says from 30 to 28%, or let's say 30 to 25%. So sometimes what happens is, so it starts deviating from 60 degrees and then maybe it is going to settle at 59.8 only, because the wall goes from 30% to 28%. Because when the 59.8 is there, what is the error? Error is 60 minus 59.8, which is 0.2. Let's assume that Kc equal to 0.1. Then what is my pressure signal? Pressure is equal to 7 plus 0.1 into 0.2. So 7.02. So the 7.02 is extremely almost there is no pressure signal. Clear? So the 28%, so that means is as it is. As it is. So this 28% will stay as it is. Correct or not? Because the system is not responding to the small errors because the Kc is small. So that is why when Kc is small, offset is possible. Because when Kc is small, the pressure signal that you create because of the small error, if the system is 59.8, the error is 0.2. So steady state is 7 and it has come to 7.02. That 0.02 has no effect on the wall. That is why this 59 point stay. So that means the controller cannot change this 59.82 as it is. Suppose when that is why now you link it to the offset problem. Now if you increase the case, same problem, if my Kc is equal to 1, then what happens? This becomes 7.2. So then the wall might change from 28. That means the system responds to even the small errors. So basically what I want to say is, when Kc is small, the system doesn't respond to smaller errors. When Kc is high, the system will respond to small errors also. So that is why when Kc increases, the offset decreases. When Kc increases, the offset decreases. Did you get? So basically what I was trying to say is, when Kc is small, so let's say, maybe I'll just explain one more time. Suppose let's say the measurement is 59.8. That means this is the system is 59.8. Then what is my error? 60 minus 59.8. So this is 0.2. Suppose if Kc equal to 0.1, then what is the pressure signal? 7 plus 0.1 into 0.2, 7.02. Does the system responds to 7.02? Because the incremental pressure is only 0.02. So pressure increased from 7 to 7.02. Does the system responds to a small value of 0.2? So system doesn't respond to 7.02 because it is as good, because 7.2 is almost equal to 7. Did everybody get this point? Same measurement of 59.2 comes if Kc is equal to, let's say, 10. Then what is my pressure? 7 plus 10 into 0.2, 9 psi. Now the system responds or not? Now system responds and makes 59.8 to 60 degrees because you have changed the pressure to 9 psi. No, that is why when Kc is low, there is a possibility of offset. When Kc is high, offset decreases. So did everybody get now? See, that is why this. See, here somebody is asking one doubt. See, when I have Kc equal to 0.1, the valve closes from 30 to 28. When I have Kc equal to 1, valve closes from 30 to 25. So 25% closing means faster response is what I am trying to say here. So Kc value is something that you have to put in when you start up the plant. So Kc that like you need to tune. That is why when you start the plant, there is a concept of tuning of the controllers. That means a new plant you have to tune according to the responses. Clear? So that is why. Now next one is proportional integral controller. What is the main objective of proportional integral controller is it eliminates the offset. It eliminates the offset. Let us see how it eliminates the offset. What is the equation that you have is P equal to Ps plus Kc into E plus Kc by tau I into integral 0 to T E into dt. Can you derive transfer function? What is transfer function here? So can you derive what is the transfer function here? Kc by tau I. Tau I is called as integral time constant. Tau I is called as integral time constant. See, these are different types of controllers: proportional, proportional integral, proportional derivative. Let's see the use later on. So what is the transfer function? P minus PS equal to Ks into D. Ks into capital E to dt. So what is the transfer function? Now let us see how this, let's say, eliminates the offset. What is the controller? Suppose let's say my field signal is 59.8. So let's see how this controller works. Let's say my measurement is 59.8. Clear? Then what is my error? 60 minus 59.8. Then what is my error is 0.2. Suppose if it is a proportional controller, then we need to compare with proportional only, no? 7 plus 0.1 into 0.2, which is 7.02. Clear? So let's take Kc equal to 0.1. If it is proportional integral controller, then what happens is 7 plus 0.1 into 0.2 plus, let's say 0.1 is K, let's say tau I is equal to 1. Let's take tau I equal to 1, integral of 0 to t into 0.2 into dt. So what happens is 7.02 plus 0.02 0.02 into T. So what is the response is the pressure signal, like if you draw the signals here, so this is my steady state 7, the P controller here and PI controller here. So the pressure signal, let's say error, this is my, let's say, error is equal to 0, then this is also 7, this is also 7. Suddenly error becomes, let's say, 0.2, error becomes 0.2. This P controller will increase by 7.02. For this 7.02, controller doesn't respond because the value is so less. This will increase 7.02 and plus the 0.02 into T. So with respect to time, the pressure signal keeps on increases. Correct or not? The pressure signal keeps on increases. So this is the one which is actually eliminating the offset. Eliminating the offset. Even for the small errors, because of this integral term which comes because this 0.02 is something which doesn't respond. Whereas later on the response keeps on increases as a function of time because of this 0.02 into T. So that is why the control valve keeps on slowly opening or slowly closing. So that is the one which eliminates the offset. Clear? So this will be keep on increasing only. At one point of time, what happens is the error is like in reality what happens is, so this is my error. Error is equal to 0. Let's say this is my PI signal that I am saying. PI signal is 7 psi. Error has become, let's say, 0.02 or let's say 0.2. Then what happens? Pressure increases and then keeps on increases. When you keep on increasing the pressure signal, the valve keep on closing. No, at one point of time, it will reach 60 and may increase beyond 60 also. Clear? At one point of time, the error will be, so along with this one, the error, let's say, has increased to 0.1. Clear? So here, if you try to see, so when error has become 0.1, so then what happens is, since the pressure is increasing, error slowly decreases. So at one point of time, error will become negative because the pressure always keep on opening. So when it is keep on opening, this is the reality that I am saying. Pressure keeps on increases. When error becomes negative, then it will be slowly decreases. Then error will become slowly again U-turn. So then once again it increases. So in reality, what happens is you will get a oscillatory response where slowly the error becomes 0. So that is where the pressure signal will also oscillate and finally settles at a new value. Why this oscillation? So like imagine a scenario, you are working as a PI controller. So then what happens is, so the moment when you see the CSTR temperature is 59.8, you go and slowly close the control valve. When you slowly, because it takes some time, no? When you close the valve, it doesn't take immediately, the temperature doesn't affect. So when you open the valve, the cooling water has to flow through the control valve and it has to affect the CSTR. So by that time, you might have opened little more. Understood? By the time, let's say the temperature is 59.8. I have slowly opened. It has become 60. So and it has become 60.2. Then you will slowly close. Then you will slowly open. Then you will slowly close. You will slowly open. That means your hand is on the control valve till you see a temperature of 60 degrees. So are you understanding? See, when the error, see, imagine that, don't look at this graphs and all. So just follow my explanations. So assume that you are working as a proportional integral controller. Then what do you do is, when you see a CSTR temperature of 59.8, you just go and put your hand on the control valve and slowly closes. So when you are slowly closing, you cannot stop exactly at 60, no, because it takes, there will be some time lag. You are opening the cooling water, but it doesn't reflect immediately on the temperature, no, it will take some time. By the time it reflects on the temperature, you might have opened the control valve little more, because this function of increasing as a function of T means you are continuously opening the valve. You are continuously opening the valve. So that means you are continuously, let's say, closing the valve or opening the valve, whatever it may be. So you are continuously closing the valve. At one point of time, you see that you will overshoot 60. That means you will see 60.1. When you see 60.1, suddenly you stop closing, you start opening. When you see slowly started opening, it will go below 60, maybe 59.9. Then you will slowly open, slowly close, slowly open, slowly close. So this kind of oscillatory behavior will be there when you will leave the hand on the control valve is when you see a temperature of 60 degrees. So are you understanding my explanation? So that is what is this actually the increasing curve. So in reality, what happens is my error starts to point to, then my pressure starts to increase, then error slowly drops, and then it drops below negative error also, then it will increase. Then this kind of oscillatory behavior is there. That is why, yeah, that is why you have oscillatory behavior, because you cannot put the control valve at a right 100%. Let's say 20, let's say right now the control valve is 30% open, system is at 60, suddenly 59.2, 59.8 is has become, then you have to close the control valve. What is the correct closing? You don't know exactly. So that is why you are doing the trial and error procedure. You are doing the trial and closes, opens, slowly closes. So you can't stop exactly at what when you see 60, because there is a time lag of opening of the valve and it is reflecting in the temperature. What are the sequence of event? I am slowly closing. When you close, cooling water increases, cooling water flow increases. That flow has to go through the jacket of CSTR. Then it has to take the heat from the CSTR. That is where it will reflect, no? So during this, let's say, time lag, you might have opened the control valve little more or closed the control valve little more. So that makes the temperature to go from 60 to 60.1. That is where when you slowly opens, you slowly closes, you slowly opens, you slowly closes. So that is how you have a oscillatory behavior. Just take time and understand the system. See, it reaches ultimately 60 here, no doubt. No offset in integral controller. When offset is not allowed in the systems, that is where you have to have an integral controllers into system. But the systems, see, the rate at which the pressure increases depends upon tau I. Suppose here you put, let's say, tau I is equal to 1, then it is 0.02 into 2. So suppose if tau I is equal to 0.1, then what happens to my P? P equal to 7 plus 0.02 plus 0.1 by 0.1. Then it becomes 0.2 into T, no? Then what happens to this one? This is my response. Then where the valve opening is might be at a faster rate. Might be at a faster rate. That is why this 1 by tau I is called as reset rate. 1 by 2 I is called as reset rate. And this controller is called as reset controller because it resets the system from where it has disturbed. There is no chance of offset here. This is called as reset rate. And this controller is called as reset controller. So you go back and name this PI controller as reset controller. Because it resets the system from where it has disturbed. Now I'm giving, let's say, 5 minutes time. Understand this controller. slowly digest the concept how it is working. So there is no technique where you can bring it to zero, or let's say that is what is the system. No, if you have a technique where you know the entire system, then there is no concept of modelings and all. TI and KC, all these values you have to tune during the plant operations. We can't say which TI is good or which TI is bad. Suppose one thing we can say is, suppose this is my, let's say, ultimate value. This is my, let's say, ultimate value. When TI high, this is how the system behaves. TI high. TI high. Suppose if TI is low, then which one reaches the, you don't know, depends upon the TI low. When TI is low, the overshoot is less. So this 1 by TI is, sorry, this is TI low, this is TI high. When TI is high, then 1 by tau I is low. The next one is proportional derivative control. So what is the action P equal? So what is the transfer function? So what is the transfer function? So P minus PS, Kc into capital E, Kc into tau D. Capital E and small e are same because steady state values are same. Capital P of S by capital E of S equal to Kc into 1 plus tau ds. This is the transfer function. So did everybody wrote till this point? I'll just write on this same board. Yes, I can create only 12 boards, I think. What the transfer function is P of S by E of S equal to Kc into 1 plus tau ds. Now how the proportional derivative controller works? Let's say my measurement is 59.8. Then what is my error? 60 minus 59.8, which is, let's say, 0.2. What is proportional controller? Let's take Kc equal to 0.1. Kc equal to 0.1, which is 7 plus 0.1 into 0.2, which is 7.02. What is proportional derivative controller is? Let's take tau d is equal to 10. Or let's say, so we'll take directly the example of I'll save this board. Okay. Suppose if my error is increasing with respect to time, let's assume that my error is increasing with respect to time. Then what is my P controller response? Kc PS plus Kc into T. What is my PD is PS plus Kc into tau D plus Kc into, or let's say Kc into T plus Kc into tau D. So that means if my error is equal to 0, my proportional controller, this is PD controller. PD controller. This gives 7 psi, this gives 7 psi. Suppose if error increases with respect to time, then what is my proportional controller is? Increases with respect to time. What is my proportional derivative controller is? It adds extra Kc into tau D on proportional action both. This is, it is adding in the upfront because error is, this is adding under the assumption that error is multiplying in future. So this is adding under the assumption that error is going to multiply in future. So this is, that is why this is called as anticipatory controller. anticipatory controller. That is why this is called as anticipatory control. This extra action which is adding, because error is going to multiply in future, no? So that is why this is adding an extra pressure signal or extra response, because error is going to multiply in the future. See, error is going to increase in the future, no? It's because it is a ramp input of error. For some reason, error is continuously increasing. So that is why this extra addition is good. But what is negative point here is, now my error is 0. Say error deviated slightly below, not because there is a disturbance, because of, let's say, small error of, let's say, 0.1, or let's say 0.2. 0.2 is a very small error. So I have not muted, no? Can you hear me? Okay. So small error, that 0.2 error might be because of some fluctuations. Only one person is saying I can't hear you, but rest of the people are saying, I think there is some problem on your side. So there is a small error of 0.2. That might be not because of process update. Maybe sometimes what happens is these measurements are also fluctuating. So if it is proportional controller, it doesn't respond at all. When Kc is equal to 0.1, it doesn't respond at all. So it doesn't respond at all when Kc equal to, this is P controller. PD controller, what happens is, even if errors fluctuates little bit, it jumps upon the pressure, because under the assumption that pressure is going to increase in the future. Suppose if it is really increasing, then it is a problem. If it is really increasing, it is a problem. Clear? So if it is really increasing, it is a problem. But in reality, it is small deviated because of some changes. So that is why this is not good. This makes the system which is in steady state to go into unsteady state because of the extra action. See, I'm taking extra action, which is good if there is really problem. Even if there is no problem, if I take extra action, that means it is not good for the system. That is why this derivative action has to be implemented carefully, has to be careful. So you have to be extremely careful when you are applying, let's say, this derivative action, because then the systems will start reacting for small errors, which are like measurement errors also. So that is why you will never see PD controller in the plant. You will always see proportional integral derivative controller. So that is why in the plants, we will never see the PD controllers, because derivative action is sometimes become dangerous. So last one is PID controller, where you have proportion, but this derivative action, so this derivative action increases the offset. This derivative action, or let's say this derivative action increases the fastness of the response. Clear? Now what is proportional controller? Integral controller, you have P equal to Kc plus Kc into E plus Kc by tau I 0 to T E dt plus Kc into tau D into dE by dt. So what is the transfer function? P of S by E of S equal to Kc into 1 plus 1 by tau is Kc into tau D. This is the transfer function. So when you need integral and derivative both, you can use the PID controller. Now let's see all the responses at one go. Suppose in the CSTR case, the inlet temperature goes from 40 degrees to 50 degrees. Then let's say 60 degrees will become 70 degrees. This is for which controller? This is for which controller? This is without control, no control action. Suppose now proportional controller. So this is how the proportional controller. So what is proportional integral controller? But eliminates the offset. What is proportional integral and derivative controller? This is PI. What is proportional integral derivative controller? It adds to the speed. It will increase the speed. This is PID control. This is for a load change. Whatever the diagram that we have done is for a load change. Proportional controller has some offset. PI doesn't have any offset. If you add, that is why I have not run any PD, because you will never use PD controller in the system. So I think we'll stop here. We'll take if you have any doubts. PID decrease of PID actually has a faster response because of the derivative action. That is why the oscillation decreases.